Welcome back. So today we'll be continuing simple harmonic motion, and today we'll be seeing some illustrations of simple harmonic motion. And the first one is the motion of a simple pendulum. So suppose we have a pendulum which has a mass of A, mass of M, and it is supported by a point O. So this point is A, and on route like moving it goes to the point P. Okay, and so the length is, so I'm writing all the points. So length is equals to L, and it is displaced from its mean position. So A is the mean position, and it is allowed to oscillate. And there is an important condition that the angular displacement is less than 4 degree. It should be less than 4 degree. This is very important. Okay, and suppose at any time of instant t, so time at any time t, so it comes to a position P. Okay, so it comes to a position P such that the displacement AP, so this AP displacement, that we consider it as x, and its angular amplitude is theta. So this is theta, and the length of the pendulum is L. We already taken it, so OA is equals to L, OA equals to L, and so then we found that it is theta. Okay, then we know that tan theta will be x by L, so tan theta equals to x by L, and since theta is very small because we already took it less than 4 degrees, so tan can be removed, so theta equals to x upon L. Now at any position P, so the weight of it is mg, so I'm just drawing a straight line, so it will be mg, so weight, that is mg, vertically downwards. So now we'll just resolve into components. So the two components will be mg cos theta and mg sin theta. So we know that whenever string is there, there is a component called tension. So T is the tension, and we'll just on 90 degree we will just split it. So this angle will also be theta, alternate angles, and this will be mg cos theta. So this is acting along the tension of the string, and this mg sin theta is acting perpendicular to the string, and it is the only force acting on the pendulum, if you see, because tension will balance mg cos theta. So this will be mg sin theta. Okay, so this is the complete drawing of it. Now let us move to a next step. So we see that force, the only force that is acting, and since we know that this side is positive of the coordinate and this is negative, so F equals to, and mg sin theta will take it minus because it is acting in this direction, so mg sin theta, negative sign is there, so we consider this as equation 1. And we can, for small theta, this sin theta can be replaced as theta. So for small angles it will become theta, and this will be mg theta. So sin theta, theta, so it will be turned like this. Now we will just consider F by m is known, acceleration F equals to ma. So F by m, this is acceleration. So here the acceleration is g, so this will be minus g theta. Okay, so we have F is coming here. Okay, I hope you are getting, this is coming here, and this is g theta, and negative sign is already present. And we already found that x equals to theta L. So the linear displacement is x equals to theta L. Now we have to write acceleration. So acceleration we'll write here. So we are writing directly. So this is just simple differentiation with respect to time. We have differentiated it twice, so we can directly write it. Now we will just compare it with the original equation. We had this one. So this was our second equation, first equation modified. So on comparing with this, we'll get L, this part right here, I'm writing this one. So this part represents acceleration, so F by m is also acceleration. So these are same, so this will be, and we'll write this value right here, minus g theta. Okay, and finally, since acceleration of Bob of that mass bob is proportional to the angular displacement, the motion will be something like this. So we'll just write it in the terms of acceleration. So this will be g upon L theta. Okay, and now what we will do is just simply write this term as equation. So we have just converted this equation in the form of omega. So omega will be g by L, omega square, that is. So this is the differential equation of a simple harmonic motion, we all know that. So we need to convert it in this form, so that acceleration and theta form, so that it will be in harmonic. So this is our final equation. Okay, and now there are some special terms. So time period will be, time period is 2 pi upon omega. Okay, and on placing the value of omega, so t will be 2 pi, and omega is what? Omega square is g by L, and 1 upon omega will be root under L upon g. So this is also an important formula for time period of the bob for oscillation of simple pendulum. So this was the motion of a simple pendulum. So if you had any problem, just comment, and if you did like the video, hit the thumbs up button and subscribe to my channel for more videos. So thanks for watching it.